Okay, now we pretty quickly saw that if we're going to do the x-coordinate versus the arc position, which is what we're going to graph, then the arc position from here to here, if the arc position is 0 here, and the arc position means distance along the arc up to the point, then up to here it's going to be pi over 2. Because it's a unit circle, meaning it has diameter 2, circumference is ratio of diameter to circumference. Pi is its ratio of circumference to diameter, so the circumference has to be 2 pi, and this is a quarter of it. Okay? And if you take a quarter of 2, you get a half, and so you have pi over 2. So this is pi over 2. And then how many divisions do we have? Well, we divided in half, then we divided the halves in half, and then we divided those in half, so we got 8 subdivisions, right? So we just say, okay, that's pi over 2. This is pi over then 16, 1/8 of this, right? And this is 2 pi over 16, and I'm just going to write it that way, 3 pi over 16, 4 pi over 16, 5 pi over 16, 6 pi over 16, and 7 pi over 16. Now 16 is a power of 2, so only the even numbers will allow us to, the multiples of 2 will allow us to simplify the fractions a little bit, right? So we can go ahead and simplify and put them in lowest terms. But if we write them down this way, we know we've got them right, even if they aren't in lowest terms, right? Because the pattern here is very simple. And then we can say, okay, that equals pi over 8. And this one equals pi over 4. And this one equals 3 pi over 8. And of course, here we have pi over 2, which is the same as 8 pi over 16, right? That's pretty simple. Okay? Now, it turns out there is one point here, just one, where we can figure out what the exact sine and cosine are. And that would be the pi over 4, because for the pi over 4, then that corresponds to the first subdivision. The two legs of the triangle are equal, and their squares have to add up to 2. So each one is equal to 1 over the square root of 2, or square root of 2 over 2, which is about 0.707. Let's see what we got. Oh, we got 0.7. Okay, that was an honest estimate. I wasn't fudging. Okay, I wasn't paying any attention to which point I had. So we do have kind of a point of reference here where we know exactly what the angle should, what the x-coordinate should be, right? Okay, so now we can sketch a graph. And okay, you're used to measuring angles in degrees, but degrees are totally unnatural unit for angle. Now they're convenient, and 360 is chosen, I think, largely because there are lots of numbers that divide 360 evenly. Okay, it's got a complex, it's got a lot of 2's and 3's in its prime factorization. Okay. So it makes it easy to subdivide 360 degrees in a lot of ways. Okay? And get even numbers for your angles. But other than that, it's kind of worthless mathematically to use degrees. I mean, it's great if you're trying to, it's much easier to think, okay, that's a 45-degree angle, think that's pi over 4. But that's what we're going to use for our angle. So I'm going to say that your angle, which I'll call theta, is your arc position on this unit circle. Okay? And what unit does the angle have here? Well, that's called radians. And in mathematics, if your angle's in radians, you don't even have to write the radians. If you write the cosine of 30, you mean the cosine of 30 radians, whether you know it or not. If you mean 30 degrees, you got to say degrees. In mathematics, if you are measuring in radians, you don't have to say anything, but you can put the radian in there if you wish. It's optional. Okay? So cosine of theta, if you just have a number for theta, that means radians. Drives me nuts to see people writing cosine of 30, although a lot of good teachers let you do that. And a lot of publications do it. I think it's not a good idea because it doesn't reinforce the idea that radian is fundamental. Okay? I mean, how much effort is there to put a little degree sign next to your angle and specify the units, right? Mm-hmm. I think it's very bad practice not to, but there are some darn good people that might disagree with me on that, so just be aware of both perspectives. Okay, so anyhow, we want to now graph the x-coordinate versus theta. So, easy to do that. Here's pi over 2, right? Mm-hmm. Well, we can just do the same subdivision we did there. Divide that in half. Divide those intervals in half. Divide those intervals in half. Now I've got 8 equal intervals that lead up to pi over 2. I don't even have to label them, but I can if I have reason to, right? Okay? And then my x-coordinate, well, there's no point on this whole circle that has an x-coordinate over 1, is there? And there's no point that has an x-coordinate less than negative 1, because of course, if you keep going around here, you start getting negative x-coordinates, right? Okay, so we have negative 1 here. Now, for these angles and these numbers, we're not going to need that, but in a minute we see what happens if we keep going, right? Okay, so now what do? Well, we just go ahead and make little marks where our points are. Let's just go ahead and put a couple of dotted lines for reference. So that's where half is going to be. This is where 1 is going to be. That'll help me locate my coordinates. So 1, and then 0.97 isn't much less than 1. I mean, 0.9 would be like here. So I'm going to put my 0.9 in here. My 0.97 is going to be up here, very close to 1. My 0.8 now, which goes with my third point, is down a bit lower. My 0.7, even a bit lower. My 0.55, that's at 1, 2, 3, 4. Am I even above this point? Yeah, I'm kind of screwing this thing up, but you get the idea. Okay, 0.55 with the fifth point would be just above here, and then a 0.4 maybe be about here, and then a 0.2 would be about here, and then we have this, and now I've got this nice smooth arc if you have good estimates, right? And if you don't have good estimates, you just do what we do when we fit curves. You follow the trend you think these points have to have, right? Just by thinking about how you got the numbers, okay? How the closer you get to here, the further you're moving over this way each time, so x is going to change by more. You know, think about what you're doing while you're doing it to get insights, which you can then express mathematically, right? Well, then you go all the way around the circle, but you know, if you think about it, you've got all the numbers you need. Okay, some of them are going to go negative. You know, when you go through this quadrant, the numbers are going to go negative on you, right? And down here, they're still going to be negative, but as you come around here, they're going to be positive again, right? And you're going to get a whole graph of a nice function, right? Anybody want to tell me what function we're graphing here?
Cosine.
It's a cosine function. Okay, if you've had trig, you know that if you haven't. But and if you graph the y-coordinates, you're going to get the sine function. Okay? So, exercise I'm asking you to do is draw a good circle, make good estimates. Okay? And get your graphs. And what does that graph have to do with the pendulum? Well, if the pendulum's swinging between here and here, it starts here, goes to here, comes back here, goes to here, right? And if your time is marching along here, this gives you your position versus time. Okay? And your slopes give you the rate of change of position versus time. Okay? You have an important graph, okay? And it kind of completes the picture of the most basic functions that we use in applications in the real world, okay? There are many more that are built on these functions and related to these functions, but if you understand power functions, exponential functions, polynomials, sums of multiples of power functions with whole number powers, quotients of polynomials, rational functions. It's all built on power functions, exponential functions, trig functions. Okay? And the trig functions are all built on the sine and cosine.